In the first example, we are asked to find the Laplace transform of an exponential function x of t equal to e minus at u of t, given that a is greater than 0. So let us visualize what is this function in time domain. So since we have a unit step function u of t, so it would be starting at 0 and moving towards the right side. E minus at, if a is greater than 0, so this means that it's going to start at 1 and then converge as time tends to infinity. This is our e minus at u of t. In order to find the Laplace transform of this, we know that x of s is minus infinity to infinity x of t, so this is simply e minus at u of t, and then this is multiplied by e minus st dt. In the second equality, we absorb the unit step function in the limits of this integration, so the integration would start from 0 and go to infinity. Next, we can combine the two exponentials, so we would have e minus s plus a t d of t. So the integration of this function is simply minus 1 over s plus a times the function for t starting from 0 and terminating at infinity. So let's put the limit, the initial limit minus when t tends to 0. In this case, when t is 0, so this whole thing would be 0, and exponential of 0 is simply 1, so we are having 1 here. So the Laplace transform is much more dependent on this limit. So at time infinity, would this function converge or diverge? So if it converges, so this means that this whole function at time infinity would have a value of 0. And if it diverges, then that would mean that this function would have a value of infinity. So when does this function has a value of 0? So this would dictate the region of convergence. We know that this function e minus s plus a as limit t tends to infinity. So this is only 0 if real part of s plus a is greater than 0. As you can see that a is real and it is greater than 0, so it is converging. So similarly over here we are saying this whole argument of an exponential s plus a. Over here we only had a, so now we have an s plus a. So s plus a should be greater than 0. So if this is true, then this is true. So this means that real part of s, the complex plane, would be greater than minus a. So that is if we plot the s plane. This is sigma and this is j omega. So we have some value which is minus a. So note that a was positive, so minus a would be on the left side. Let's say this is minus a. So this function suggests that real part of s should be greater than minus a. If we draw a line here, so our s should be in this region. So hence we can say that our region of convergence, that is ROC, is such that the real part of s is greater than minus a. So for this region of convergence, the algebraic expression x of s is simply 1 over s plus a. A is something that we call as pole, which are in the denominator in this rational function, and they suggest that for our given case, if we set s is equal to minus a, so in that case, if this is minus a and this is plus a, so we would have 1 by 0 and x of s would go to infinity. So the poles determine when this function x of s would go to infinity. So in short, this algebraic expression which contains one pole at minus a, which we have represented in terms of a cross. So this would converge only if the value of s is greater than minus a, right? So it's on the left side, on this direction. It cannot be at minus a, because if it is on minus a, the overall value of x of s would approach infinity. So poles are not included in the region of convergence. So we can say that x of t e minus at u of t for a greater than 0. So the Laplace transform x of s is simply 1 over s plus a, and the ROC, region of convergence, is real part of s is greater than minus a. So in the second case, we have x of t equal to e minus at u minus t for a greater than 0. This was right-sided u of t, this is left-sided u of minus t. So if we plot this in time domain, because of u of minus t, so this would be on the left side. So this function would have some sort of this plot. This is minus e minus at u of minus t. Again, if we take the Laplace transform of this function, so x of s from minus infinity to infinity. So minus infinity, rather than writing infinity here, we can simply write u of minus t. So this would go until 0, After that, the value doesn't exist. So we don't need to take the Laplace transform beyond that. So we have a minus here, and then e minus s plus a. Again, if we integrate this, we would have 1 over s plus a, and the limits would be minus infinity to 0. Again, if we put the time equal to 0, so this whole thing would simply be 1. But we are interested when this function converges. So it would converge when we have a value of 0 over here, when time is minus infinity. So that is when limit t tends to minus infinity, e minus s plus a t would be 0. So to understand when this function would be 0, let us look into this original plot, which says that we have value minus e minus at u of minus t. So if we remove this minus sign here, the first minus sign here, so we would simply have this function. This is e minus at u of minus t for a greater than 0. But if it was to converge, this a should be negative, that is a should be less than 0, right? So for that case, we would have simply this function. Note that again we have e minus at u of minus t. So this is something which we are having over here. From this intuition, we can say that real part of s plus a should be less than 0 for it to converge. So this is true when our region of convergence ROC, it suggests that real part of s is less than minus a, and in that case our algebraic expression is 1 over s plus a. This is x of s. Again, in terms of an s plane, we have sigma and j omega, where our pole is at s equal to minus a. So this is minus a. The region of convergence is to the left of minus a. So again, we can draw a line at the pole, and this suggests that this is our region of convergence. Again, note that the ROC does not include the pole, that is when s is equal to minus a, because in that case x of s would reach infinity. So some interesting points in these two examples. The first one was e minus at u of t for a greater than 0. So in this case, the algebraic expression 1 over s plus a is exactly similar as for our second example when we have minus e minus at u of minus t. So 1 over s plus a and 1 over s plus a, they are exactly similar. There is no change. But the change appears in the region of convergence. Previously, this was the pole and this was the region of convergence. But right now, in the second case, for this pole, the region of convergence is towards the left side of the pole. So in S domain, you need both ROC and the algebraic expression to understand given signal or a system fully. So next we have x of t equal to in order to take the Laplace transform of this function, that is capital X of S, we can take the Laplace transform of this and then add with the Laplace transform of this to eventually get the solution. So this would simply be 3, and because of this u of t start from 0 to infinity, and similarly we would have minus 2. Because of u of t we would have 0 to infinity e minus s plus 2 e dt, and this would be if you look back to example 1, that is e minus at u of t is simply 1 over s plus a, and the region of convergence real part of s should be greater than a. So for this case it would be 2. So from example 1 we can simply say this is 3 over s plus 2, and this is valid when the real part of s is greater than minus 2 minus 2 over s plus 1, and this is valid when our real part of s is greater than minus 1. Or simply you can say this is 3 over s plus 2 minus 2 over s plus 1, and this ROC suggests that the real part of s should be greater than minus 2, and it includes this minus 1. As the combination, we're going to take the leftmost pole for this particular case because ROC is on this side for this as well as this. So that is, we have two poles. The first one is at minus 1, is coming from here, and the second pole is at minus 2. This is sigma and this is j omega. Since both of them are in this direction, so this means that we can sketch a line and say that our ROC for this particular case is towards the right side. That is right of the rightmost pole. Both the signals are right-sided. So we can combine these two together and we can say that real part of S would be greater than minus 1. If this was left-sided u of minus t and this was also left-sided u of minus t, so in that case the ROC would be minus 2 and towards the left of it. If we take the LCM, we have S plus 1 plus 2, and if you cross multiply, so you will get S minus 1. So we have x of s, which is a rational function in terms of the numerator, which has a polynomial of s, and denominator having a polynomial s as well. So these two identify the poles, and this identifies the 0. So presently our 0 is at s equal to 1, right? So if this was 1, so we can draw a 0 over here. So we usually draw a circle to represent a 0 and a cross to represent a 1. So what does 0 mean? 0 means that if you set the value s equal to 1, right, that is at s equal to 1, the numerator will become 0, and hence this signal would become 0. So therefore zeros are making the signal 0 and the poles are making the signal infinite at their respective points. So for the fourth example, say this whole thing remains the same, plus we add another function, say delta of t. So we know that the Laplace transform of this is now obtained as this, and we have this region of convergence. So if we add this with the Laplace transform of delta of t, we should get the solution. Let us proceed to that. That is the fourth example. This is already done, so we won't do it again. Let's do the Laplace transform for this function. Let's call this as x1 of t. So x1 of s is simply minus infinity to infinity e minus st x of x1 of t dt. But this is simply delta of t dt. Delta of t is only valid at time 0. For rest of the time the value is 0, and for time 0 we have an impulse. This means that if we multiply these two signals together, this t would turn to 0, and simply we can say this whole thing is e minus s times 0, and this is minus infinity to infinity of t dt. The exponential of 0 is simply 1, and the area of direct delta function is also 1. So we have just 1. Hence x of s is this x1 of s plus, say, this was x2 of t, which we have already calculated over here. This is x2 of s, and hence we have 1 plus s minus 1 over s plus 1 s plus 2. But before going to that, x1 of s, so it says that it has a value of 1. But what about the ROC? So this says that this is 1 irrespective of any value of s. So for all values of s, the x1 of s would be equal to 1. We can simply say for all s. So the whole s plane is the region of convergence. This also gives us a very interesting and a very beautiful property that if the signal is finite, x of t is finite in time. This is finite in time, only available at time 0. This would lead to x of s having an ROC of entire s plane. This is right-sided, so the ROC was right-sided. If it was left-sided, the ROC is left-sided. If the signal in time domain is finite, the ROC is the entire s plane. So coming back to our present example, we have 1 plus s minus 1 over s plus 1 plus s plus 2, and by solving that you would have s square plus 4s plus 1 s plus 1 and s plus 2. So we can find the roots of numerator from the solution of quadratic equation, and that would be simply and from here we can find the s plane or the region of convergence. So For x2 of s, we have already identified that the region of convergence should be greater than -1. So for this, it should be greater than -1, and x1 of s is saying that the s could be anywhere. So we have a pole at -1 and then another pole at -2. So as the overlapping region would still be the same, but we also have zeros over here. The first zero is around here, which is when the value is -2 plus under root 3, and similarly we would have some value over here which is -2 minus under root 3. So two zeros and two poles. So for all the LTI systems that we have considered, the poles and the zeros would be either real or they would be conjugate pairs. For example, for another case, if we have a pole over here, right, which is complex, so we would have a pair, so we would have a conjugate pair, the second pole appearing over here. Similarly, if we have a zero appearing over here, so this would mean that we have another zero which is a conjugate pair. So these were some of the examples of Laplace transform. In the next video, we would be looking into the properties of region of convergence for the Laplace transform.